Hello everyone. So today we're going to talk about the motion of charged particles in electric fields. So far, if you'll recall, we've talked about how electric fields are created by electric charges or between parallel plates. And those are kind of the two limiting cases that we talk about in this course. We either talk about single electric charges or a collection of electric charges that's maybe spherical, so it's kind of like it acts in a sense like a single electric charge, just with maybe a larger charge. Or a special geometry where we have two parallel plates where there's a positive charge on one plate and a negative charge on the other. So those are the two basic geometries. And to remind you, the electric field lines are always drawn in such a way as to show which way a positive electric test charge would move. So if we were to actually take a charged particle, such as perhaps an electron or a proton, and place it in that electric field, then it would experience a force, right, a Coulomb force, and it would accelerate. So two of the things that we're going to use in these kinds of problems, are Newton's second law, depending on whether we want to talk about, let's say, vector-based issues or vector-based characteristics, or the work energy theorem, where we're talking more about scalar-based. So one of the things, at the start of this course, one of the things that I talked to you about is that there are three big laws, right? Those are Newton's second law, the law of conservation of momentum, and the law of conservation of energy, or the work energy theorem. And as expressed. And so really you have to think about which one to apply based on what it is you're looking for. So in this case, I just want to have you remember that Newton's second law we tend to use when we're looking for anything that's involving a vector that's not in response to a collision, right? If we have a collision, then you typically use the law of conservation of momentum. But if it's not a vector, if it's not a collision rather, but there's still some vector component going on that you need to work out, then it's usually Newton's second law. However, if you're looking for something that's scalar, like a speed, for instance, then typically you're going to use the work energy theorem or the law of conservation of energy. Okay, so enough preamble. Let's go on. So let's say if we have a fixed charged particle. So a situation where we might have is we have a free to move charge Q1 is placed near a fixed, meaning that it cannot move, charged particle Q2. What happens? So here's a situation, right? So Q2 is the one on the left. That's the one that's not allowed to move. Q1 is the one on the right, and you can see that it starts initially at some distance R1 at rest, right? V1 is 0 there. But sometime later, it's at position R2, and it has V2, right? It has some speed or velocity, depending on what it is we're looking for. Also notice that these two charges both have the same sign, right? They're both positive charges. So in this case, just knowing the law of electric charges, that these should repel each other. So that's basically what should happen. So, okay, so we're going to start with that assumption that we're positive, that both charges are positively charged, because that's what it is in the diagram. And we know from our law of electric charges that the opposite signs repel. Sorry, I apologize. Same signs repel. Same charges repel. And so we're going to, and so the Q1, the one that's free to move, is going to accelerate away. Here's a little bit of a wrinkle, though. So you might say, okay, well, so there's going to be a force, it's going to accelerate, Newton's second law looks to be good. Here's the wrinkle. Newton's second law really works best, at least with the math that we have at our disposal, when the force is a constant force. And in this case, it's not a constant force, right? I want you to remember that the Coulomb's law is an inverse square law, meaning that it really matters how close you are, how close Q1 is in this case to Q2. And so when it's at the first distance, right, when it's at distance R1, it will experience a larger force than when it's at distance R2. So since that distance changes, that means that the force is going to change. And since the force is changing, that means the acceleration will change, or the way it's stated here, the force will not be constant. So that means that Newton's second law is not an ideal thing to use in this case, unfortunately, right? Again, should you take physics or engineering in university, or math, I suppose, then you'll find more advanced ways to get around this sort of thing. But for us right now, if we ever have a force that's not constant, meaning that the acceleration is not constant, then we're a little bit stuck, right? Luckily, we have other tools at our disposal, and one of them is our work energy theorem. So we're gonna look at this through the lens of energy. Okay, so since there's no external force, right? Everything, all the forces here, like the Coulomb force, that's internal to what we would consider the system. So there's no external force, we don't have to worry about work. And we're just going to apply our law of conservation of energy, meaning that the total energy that in the system at the start is going to be equal to the energy in the system at the end. Again, we're going to assume that there's no external force, including friction, so there's no wasted energy. All right, so in each case, the energy is going to be a sum of the electric energy and the kinetic energy. Okay, the electric energy meaning that energy coming from the Coulomb interaction, and the kinetic energy, of course, coming from something that's moving. So breaking that down, we have our usual situations here, and the only thing that's different on the two sides is, I suppose I could have used V1 and V2, but that's okay, I didn't. I wanted to use prime in this case. So on the left side of the equation, you can see that my electric energy is at R1, right, at the distance of R1, but on the right side of the equation, I've changed it so that I'm at R2. And the speed in each case is like at the beginning of the interaction, the speed is just V, and at the end of the interaction, the speed is V prime, whatever. Notice in this equation, you have this m, right, the mass. That's the mass of the moving particle, right? Obviously, the mass, because that's the only thing that gets to move in this system. The fixed charge doesn't move. Okay, so we can apply a little bit of algebra here. In this case, I've just taken both of the energy terms, the electric energy terms, and shoved them to the left side of the equation. I've taken the two kinetic energy terms and shoved them to the right side of the equation. A little bit of factoring, and I get a nice expression here. Okay, well, it's kind of nice. So at this point, you have some options as to what you might want to look for, but keep in mind that if I'm going to look for something, it's got to be something in this equation, right? So I could look for example, the charge on one of the two charges, right? The moving one or the fixed one. I could maybe try and figure out the distance, but honestly, because I have I have this difference divided by a product, R2 minus R1 divided by R1 minus R1 times R2, sorry. That's going to be pretty annoying to figure out. I could, I suppose, figure out the mass of the moving charge, or I could figure out one of the speeds, right? So that's what I'm going to do in this case, right? In this case, I'm going to apply this formula to a sample problem where I've got two conducting spheres that are placed 25 centimeters apart, and they each have these charges, right, which you can read, right? The one that's fixed has a charge of 3 microcoulombs. The other one has a charge of 5 microcoulombs, and the one that's going to move has a mass of 150 grams. And the question is, how fast will the free sphere be moving when the spheres are 65 centimeters apart, right? So again, they're close together at the start. They're 25 centimeters apart, but then because of the Coulomb repulsion, the free sphere is going to move. And so we want to know how fast is it going to move when it's 65 centimeters apart. Okay, so I'm going to take the same equation that I started with in the last slide. And so in this case, it says the question is, how fast will the free sphere be moving? Well, that in my formula is V prime. So I want to take my formula, do a little bit of algebra here, and isolate for V prime. So if you can imagine how I might do that, think about how you're going to apply your tools and techniques of algebra to isolate for V prime. Okay, so why not pause the video and actually do it yourself? Okay, hopefully you're back, and hopefully you got this result. You realize that V, the starting speed, is actually 0 because the sphere that's moving is initially at rest. I think it says that. Yeah, the other sphere is at rest. Yeah, there it is. So that means that v is 0, which makes things quite a bit easier, because now all you need to do is multiply both sides of the equation by 2, divide both sides by m, and then square root both sides, and away you go. So it looks a little gross, but there it is. And if you plug in the numbers and do everything properly, then you get 0.07 meters per second. Okay, so hopefully that's what you got. All right, let's take a little. So it's fine if we're going to talk about single point charges and how those are going to work, but again, for us as physicists and potentially future engineers, we want to think about more of a parallel plate geometry, because there's something that the parallel plate geometry offers us that the a free charge doesn't, and that is that between the parallel plates we have a constant electric field. Okay, that constant electric field, that means the math becomes so much easier, because now we can actually apply Newton's second law should we choose to do so. So really this parallel plate geometry is something that's really going to be valuable to us. The other thing we need to consider is that the parallel plate geometry can be applied in two kind of limiting cases. One where our particle is moving parallel to the electric field, which means it's moving from, let's say, one plate to the other, which you normally use to speed up, to give a particle more speed, right? Speed it up. Or the particle could be perpendicular to the electric field, so it's moving between the plates, and like that is to say, parallel to the plates, which is this geometry you use in order to deflect the particle. So this might seem a little weird, like how the heck does this work? So here's two pictures. Here's the first picture where where the particle is traveling parallel to the electric field. So again, I want to remind you that the electric field lines in blue in this diagram are always drawn from the positive plate to the negative plate, right? It's where would a positive charge do? Or where would it go, rather? So in this case, a positive charge would go from the positive plate to the negative plate. However, in this question, or at least, sorry, I took this diagram from a question in the textbook. In this diagram, I actually have an electron, and an electron has a negative charge. So an electron would travel opposite to the direction implied by the field lines, right? And that's because it's not positive, it's negative, so everything works backwards. But anyway, in this case, you can see that the electron's motion drawn with the red vector is going to be going from the negative plate to the positive plate, and so this is a way of basically giving accelerating an electron and giving it some kinetic energy. So this turns out to be pretty useful. We'll do a sample problem with this in a second. The second geometry is this one. And so in this case, I have the two plates, again, parallel, drawn the same way. And so the field lines are drawn the same way from the positive plate to the negative plate. But the electron is traveling parallel to the plates, right? It's traveling between them, but it still experiences that force. And in this case, that force will make it, of course, repel from the negative plate or towards the positive plate, depending on how you want to think about it. And so in this case, there will be a deflection going on. Right? It will not. The electron will not leave the plates going in the same direction as it was. There's an unbalanced force going on here, so the electron's motion will be deflected. So both of these two geometries are actually useful in real practical applications. When I was younger, everyone who had a television had one of these big old tube TVs, right? And so you've probably seen them. I think we still have one in the classroom. So they're quite a bit thicker than the standard monitors that we use nowadays, which are quite thin. But the old ones had tubes in them, vacuum tubes, or cathode ray tubes as they're called. And so the idea there is that the picture was formed in the cathode ray tube by shooting electrons from one end of the tube to the other, and at the other end of the tube is where the screen was. And so when the electron would hit the screen, it would basically glow a little bit, and you'd have this phosphorescent image. If you've ever seen an old oscilloscope, they work the same way. So anyway, it's a little bit of old technology, but nevertheless, in those old cathode ray tubes, these two configurations, the parallel plate geometry configurations, were used to both accelerate the electrons and also to deflect them, so that you could actually draw images on your screen. Okay, so that leads us into sample problem 2. Okay, so in here we're talking about an alpha particle. So an alpha particle, if you remember, is basically the same thing as the helium nucleus. So it has 2 protons and 2 neutrons. That's what makes up an alpha particle. So it says here it has a positive charge of 2e. In this case, remember, E is the elementary charge, and it has the mass, and it has a mass given there. So that's basically the four nucleons added together, more or less. I guess less, actually. And it says, with what speed would an alpha particle reach the negative plate of a parallel plate apparatus with a potential difference of 2 kilovolts if it started from the positive plate and it started halfway between the plates? So in this case, just to go back a second here, we're talking about this situation. So instead of the electron in this picture, I'm actually going to be firing an alpha particle. And instead of starting at the negative plate, as it is in the diagram, I'll be starting from the positive plate. But this picture is basically what we're talking about. Okay, so let's say here we have an alpha particle, and it's going to go from the negative plate. Sorry, it's going to go from the positive plate to the negative plate. And all I know is that there's a potential difference between the plates of 2 kilovolts. Okay, so let's think about that. Again, since we're talking about speed, careful, a close reading of the question will actually tell you what we're trying to find here. And so in this case, it says we're looking for the speed. So speed is a scalar. So let's use a scalar description. In this case, the law of conservation of energy. So whatever energy I had at the start has got to be equal to the energy that I had at the end. Now, the energy, the electric energy, is what I'm going to have at the beginning. So basically, there's going to be some electric energy that really some work, I should say, that the electric field between the plates will do on that alpha particle. It's going to do some work. There's going to be a force on the alpha particle, and it's going to be over the distance. Now, which is fine, but the other way of thinking about the work done in this case is just the charge multiplied by the potential difference. So this is, again, one of the nice things about a parallel plate is that the work calculation is really straightforward. On the right side of the equation, I have my kinetic energy, right? And again, that m is going to be the mass of the alpha particle, and the v prime is going to be the final speed. So just doing a little bit of algebra here, it gives me the equation for the final speed. And then if I plug in the numbers, again, making sure that I actually have everything in the base units. So the 2 kilovolts, for example, I need to make sure that's in volts. So have that 10 to the 3 multiplier there. And the charge, it says it has the alpha particle has a charge of positive charge of 2e. So that's why in my equation here in the first set of brackets I have 2, right, for 2, times e. That's the elementary charge, 1.6 times 10 to the negative 19 coulombs. Anyway, then divide that by the mass and get that answer. 4.4 times 10 to the 5 meters per second. So one thing to really note here is that you can, just by applying a potential difference of 2,000 volts, which I know that sounds like a lot, but in the grand scheme of things, it's not that much. But you can apply a potential difference of 2,000 volts, and you can get tremendous speeds. And an alpha particle actually has a fair bit of mass. So if you imagine doing this with something like an electron, you would get an even greater speed, which is, anyway, one thing that we'll talk about. These kinds of speeds that you can ultimately get to is something we'll talk about later when we get to cyclotrons and other kinds of fancy devices. Okay, so that's the deal if it started from the positive plate. Now for B, it says it started halfway between the plates. Now again, we don't know how far apart the plates are, but it turns out that doesn't matter, because all that matters actually, if you look at the equation, right? If we go back to the equation, oops, sorry. If you go back to that equation right there, you'll see that the distance between the plates never plays a role. All that plays a role is the potential between the plates. So if we know the potential difference between the plates is 2 kilovolts, what do you suppose the potential difference is between, say, halfway between the plates and the negative plate. I mean, just take a guess, right? It's a linear relationship, which may not be obvious, but basically it's got to be a potential difference of 1 kilovolt. If you basically started halfway between the plates, if that's your starting point, then that means that your potential difference is only going to be half what the full potential difference is. Anyway, so if you repeat the calculation with that number, then you'll get, of course, a smaller speed, but it won't be like half as much of the speed, right? It doesn't follow that kind of relationship. Anywho, okay, so here are some problems that I think you should be able to try and solve. And again, what I really want you to think about when you're doing these problems is carefully read the question and decide, does it make more sense to try and solve this using a Newton's second law situation, solve it using Newton's second law, or can it be done with energy? In most cases, I think you'll find that energy is going to be the most successful strategy, but there are one or two where you actually are going to have to use a little bit of Newton's second law. So just check those out, and I will see you later.